All right, welcome back to Ecology. So I had things set up a little differently today. What I'd like to do is go through that take-home exam, which has now been graded, and then do a little bit of lecture material. So I've got things projected onto the screen so we can work with that exam on the whiteboard. All right, so the first question, the following are data from queen conch populations in the Bahamas from 2 years, 1995 and 2011. So the white circles 2011, the dark circles 1995. You can see that for both years the pattern is pretty much the same. There seems to be low percentage of adults mating based on the log of the adult population size, right? It's plotted as an absolute density. That's the number of individuals per area. We could think of this effectively as the log of the size of the adult population if we kept the area constant for all measures. And it looks like there's some critical density here below which none of the adults are mating. And then at higher densities, at least it looks to me, maybe for the dark circles it looks like this, and maybe for the white ones it looks like that. But if we distill down each of these 2 years, it looks like there is no mating that takes place at low population densities. And as we reach some critical population density, the percentage of adults mating begins to increase as population size increases. Okay? All right, so that's just taking a look at the plot. A, is there evidence for an Ali effect in the above conch data? Well, the Ali effect says that instead of being able to assume a very simple linear relationship between B, the birth rate, and the population size, where for density-dependent populations, we expect this sort of a relationship. The Ali effect predicts that at low population size, there is this precipitous drop in the birth rate such that you don't get the highest birth rate at the lowest population size. Examples of this I gave in class were passenger pigeons and other social animals that they derive a benefit from being in groups, and one of the benefits seems to be an increase in the birth rate. For conch, they're large mollusks. You think of like conch shells people blow and make the horn sound. It's probably just, if they're at really low densities, because they crawl around at the speed of a snail, they can't find each other. So they need to be at high enough densities that they run into each other and then mating can occur. So this is the Ali effect. Really precipitous drop or very low birth rate at the low population size. Well, this plot is plotted differently than this one, but the percentage of adults mating is probably a good analog for the birth rate, and the log of the population size, the log of the adult density is probably a good analog for the population size itself. So this piece of our plot is the Ali effect, right? That's that really low birth rate at low population sizes. Okay, so let me move down here. All right, the authors are using percentage of adults, just like I said, rather than the birth rate directly. And they're using it as a way to estimate the birth rate. On the figure below, plot the birth rate against population size for conch based on the data above. Please include data points well above 10 to the 4th individuals per hectare. So this is the birth rate, and this is the log of the population size. The idea here is that these low values, 1.7, that we had no birth rate. Then up to let's say 4, we had this increase in reproduction. And then I'm interested to see what you do after that. Okay? If the population is behaving the way we kind of expect populations to behave, at some point you put too many individuals in a population, resources are being distributed among too many individuals, birth rates are going to drop because individuals have trouble getting enough resources. So the most common things people did was to continue the curve down like that. I like to see this. This is this recognition of density dependence. If you did that, I'm okay with that, right? But I did not like this one because all of you indicated that the conch would best be modeled using density-dependent growth, and therefore I expect this plot to reflect this argument of density dependence. Okay? All right, number 2. You're studying a beautiful and rare species of praying mantis. God knows why. All right, populations of this mantid live on a set of islands and on an adjacent mainland that serves as a permanent source of colonists. You can assume that the mainland is the only source of colonists. Therefore, we're dealing with that core satellite model where the core population serves as the source of immigrants to the rest of the population. I think the equation that we're dealing with is an immigration rate plus an immigration rate divided by an immigration plus extinction rate. So we're dealing with this model, core satellite, we're dealing with this equation. Okay? If the rate of immigration is 0.2 and the probability of extinction is 0.4, that would give us a 0.2 over 0.6 equals 0.3, repeating. That would be the fraction of islands occupied at equilibrium. A developer is preparing to pave over the mainland area for a new amusement park. To appease local environmental groups, the developer promises to set aside the islands as a permanent praying mantis nature reserve. Assuming that the probability of extinction on each island is 0.4 and the immigration is 0.2, predict the fate of the island populations after the mainland population is eliminated. So these values come from up here, but what happens once we eliminate the island or the main source of the colonists? If we eliminate the mainland, what happens to the immigration? Well, the immigration goes to 0 because it's the only source of colonists. Therefore, we would have a model that looks like this. The fraction of islands that we expect to be occupied is 0, and therefore the fate of the island populations after the mainland population is eliminated would be they're going to go extinct. There's no way around it. Okay? All right. Oops. Move down here to question 3. All right, endangered population of 99 lungfish lives in a single population. One proposal for conserving the lungfish population is to split it into 3 populations of 33 each. Okay, you know from your demographic studies that decreasing the lungfish population from 99 to 33 individuals will increase the yearly risk of extinction from 8 to 45%. All right, so in the short run, is it better to retain the population as 1 or to split it 3 ways? Now, I set the math up this way on purpose. I like to do this because if I didn't include any math, the conclusion would be, well, you split them up into 3 because metapopulations tend to decrease the risk of extinction. But that's only if the probability of extinction stays the same. I've changed the probability of extinction to try to force you to do the math. which is also why I did this hint, do the math. The math makes things a little bit easier. So if I take 1 minus the probability of extinction for one population, this is 1 minus 8% to the first, which equals a 92% chance that the population will be there in the following year. Okay? This one, we've got 1 minus 0.45, but this is raised to the third because we're dealing with 3 populations here. So let me pull up my calculator. 0.45 times 0.45 times 0.45. That's 0.091. 1 minus 0.091. That would be equal to 0.909. Right, roughly 91% chance that the population is going to be there in the following year. This is the best math to use because that's the one that allows us to deal with changing the number of populations with the same number of individuals. It's better to retain it as one population because there's a slightly higher probability of persistence. Some of you did some other math, you incorporated the other formula into it. I get it, if you want to project things out into the future to see what's going to happen, this is probably the best approach. The problem is we don't have an equation that deals with both time and number of subpopulations. A few of you just took the equation for time and pretended it was for multiple populations, okay? Which you could do, but nobody did, if you do each of these separately with the 0.45 over time, and then group those 3 values back together again. Okay? But that's the best approach given the equations that I gave you. All right, gotta get back to here again. All right, the figure above plots the intensity of intraspecific competition as a function of light availability for a species of plant. Assume that the 2 variables are negatively related. That is, there's a relationship that predicts competition intensity based on light availability. That means that at low light availability, there is increased average above ground competition, and at high light availabilities, there's low competition. So this is just a simple discussion of the intensity of competition is expected to change based on the availability of resources. The more resources that are available per individual, the less competition occurs. The less resource available per individual, the more competition occurs. Okay? So something about competition intensity varying with availability of a resource, and the fact that that's exactly what's predicted by this plot. Okay? 2 genotypes allocate the same proportion of their acquired energy to reproduction, that's their resources, but one produces a single large offspring while the other produces many small offspring. So this is predicted in species that are K-selected, and this situation is predicted for species that are R-selected. I'm using that language because a lot of you went to that language when you answered the question. Which of these genotypes would be favored in a habitat with high density independent mortality? So there's density independent mortality, and then there's density dependent mortality. Density dependent mortality suggests that the mortality depends on the density of individuals. As you add more individuals to the population, you increase the death rate. On the other hand, if we have density-independent mortality, that means that the death rate doesn't have anything to do with the population size. Instead, it has to do with other factors, and many of you talked about these. Density-independent mortality factors are more random factors, things like fire, flood, famine, war, earthquakes, volcanic eruptions, etc., where individuals are being taken out, but the ones that get taken out has nothing to do with the size of the population. In mortality that depends on population size, you have a harder time when the population size is large, an easier time, that is lower death rate, when the population size is small. K-selected species, the species that produces this one large offspring, this individual has lots of resources that allow it to deal in an environment where it's tough to gather resources. These individuals do better in this kind of an environment where the death rate is independent of population size. So the correct answer here is it's probably better to produce lots of little tiny offspring than it is to produce one big one, because the density is independent of population size. You gain no advantage by having these extra resources with density-independent mortality. On the other hand, one of these individuals is probably going to survive just by chance. The other ones are all over the place. They may get taken out by chance as well. Okay? All right, the ability to disperse is often considered to be an adaptation. We talked a lot about that. The ability to move to other populations spreads the risk of extinction for a species. For an individual, the benefit of dispersing is if you're in a habitat where resources are hard to find, maybe by moving to a new habitat that has fewer individuals in it, things might be a little bit better there, right? Or getting away from individuals where they're passing diseases around, et cetera, et cetera. As an aside, a lot of people talked about viruses in here. I thought that was kind of interesting. Viruses must be on your mind. And part B, under what circumstances would the ability to disperse be considered a liability? Well, if the advantage of dispersal is being able to get you to a better place,